Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, let's start. It's my pleasure to introduce Julia Hockemeyer. She's an assistant professor at UIUC. She is known for her work in computational linguistics and as well as NLP. I look at Julia really as one of the pioneers in the language and vision space. She had the courage to go into this space before object detection and recognition actually started working with deep learning. So it takes a lot of courage to do that. And she also popularized one of the more interesting methods for doing image captioning, which is posing it as a ranking task. So I'm really curious what Julia is going to be talking about today. Unfortunately, she wasn't able to join us live, but she is going to be joining us via Skype. So take it away, Julia.
Hi everybody. It's a real pleasure to be able to talk to you. Unfortunately, I can't actually see you at all. So this is going to be probably a little bit weird. I can hear you well. So I don't know whether I can hear the audience. If somebody wants to say something from the audience. Okay, I can hear that. Great, thanks. So if you have any questions, you can try to interrupt me. Okay, it's, So I'm delighted to be able to speak to you. I wanted to sort of take stock a little bit about, so there's been a lot of work on image description over the last year, especially, that's received a lot of publicity, right, as we all know. And I just want to sort of take a step back and think about sort of where we're at. What, have we actually solved this task? What are the next steps? And so on. So just to remind everybody, right, image description means being able to associate images with complete sentences in English that describe what's going on in the image, right? So, and of course, there's sort of, there's more or less detailed descriptions that are appropriate for an image. Some descriptions, like the second one here on the slide, might be a little bit wrong, right? You might think this is rugby when it's American football, but it's probably still sort of an okay-ish description. It's clearly not a dog is running on the beach, though, right? Right. So, and really, this variety of possible descriptions that are all correct is what makes this task really, really challenging in a way. Right? It makes it challenging to develop systems for. It makes it challenging to also evaluate in particular, right? Because there is not one gold truth, right? This is not like classification. This is much, much harder, right? So of course, the big question is, how would you get a computer to describe images, right? So when we started this more than 5 years ago, we first thought about essentially thinking about a symbolic semantic representation or an explicit semantic representation. And we were doing this on a very, very, very small data set, the Pascal data set, which I'll talk about in a minute. So we could get away with a really, really toy semantic space, right? So we thought about, okay, images, they have an entity, they have a scene, and they have some action. And there's only a small number of these, and therefore we can build a very, very simple model. And we can just learn this mapping to this very explicit meaning representation space directly, right? And that worked sort of reasonably well. There's been a lot of follow-on work on this with much more, realistic and complex semantic representations. So that's one way of going about this, and I'll get back to this probably towards the end of the talk. But then we also realized that so one problem with this explicit semantic representation is that, at least the way we formalized it at the time, it was sort of very limiting in a way, right? You really had to predefine the space. You had very few predicates, right? It was a very, very sort of, small world, right? Instead of doing that, we thought perhaps you can do something else. We looked at techniques that are able to map two different kinds of spaces to a common vector space, right? Which is often called sort of a shared semantic space. So here's, so pictorially, the idea is that you induce a mapping from images to this vector space, and you also concurrently induce a mapping from captions to the semantic space. And then because they both live in the same space, you can measure the distances from images to captions or vice versa, just via standard cosine distance, for example, right? Right. So the technique we used was kernel canonical correlation analysis, or KCCA, right? And then so this induces this mapping, and then at test time, right, you map both unseen images and captions into the space, and then you can rank sentences, for example, by the distance to the query image, or vice versa, right? So you have the same model for image description as well as for image search, right? So, of course, even if you know how to learn this mathematically, you still need to be able to learn this from some data, right? So we need to get data sets to actually develop this task. So, of course, images are really easy to get, right? There's billions of them on the web, but that's not a problem. The problem is, of course, where do we get the captions from? Well, you might say, okay, if you go to like Flickr, for example, which is the website we've mostly been using, there's a lot of text on the site, right? It's associated with the images. So there's tags, and there's also descriptions, right? But unfortunately, none of these descriptions really say what we would like the computer to say for this image, right? None of these captions say there's a man petting a stingray, right? Which is sort of one of the very many plausible descriptions, right? The fact that this was a Discovery Cove in Orlando is really kind of immaterial, right? This provides additional context, but doesn't actually describe the image in a way that we want the computer to be able to do, right? So these descriptions are really not appropriate for the task we're interested in, right? Right. So why is this? Well, so the reason why people don't actually describe their own images has to do sort of with a very basic principle of communication, right? They're called the Gracian maxims, namely, you want to be informative, right? Or you don't want to bore your the people you're talking to or the people you're writing for in this case, right? So of course, other people can see what's going on in the image. They don't need the description, right, that we want the computer to produce. Therefore, what we have to do is actually collect our own captions, right? And we use crowdsourcing because we wanted to do this at a fairly large scale. And that seemed to work surprisingly well, right? With enough quality controls in place, it turns out you can actually do this. So we started out with just 1,000 images from the Pascal 2008 challenge. So I think this was like 20 different object categories and 50 images per category. And then we collected 5 captions per image. So just to give you some examples of how this data looks like, right? So for example, here we have a picture of a plane, right? Or a picture of a bird, right? So in a way, this data set, so a lot of people have used this data set, even though it's really quite small with only 1,000 images. But I'm really an NLP person, and I was really more interested in like descriptions of events and so on. So, and I felt that this data set wasn't all that interesting. We really wanted to have more images of people doing things, right, or possibly animals. Right. So then we started actually going to Flickr and collecting images there. We started out with Flickr 8K, right? So that's about 8,000 Flickr images. Again, 5 captions per image, crowdsourced, which we've since extended to what's now often called Flickr 30K, which is about 32,000 images. Again, with 5 captions per image. And there we really try to capture a very wide variety of what people do, right? Different. So actually, the images you see here in the background are all taken from this data set. The other advantage of Flickr 30K is also that essentially all of the images are have are Creative Commons licensed, right? So we can actually distribute the images easily, right? So that's that made it a bit more difficult to select these images, but we think in the long term it makes it much easier to maintain the data set, right? So again, here are some examples from this data set, right? So here's an image of like a hockey game, right? A bunch of teenagers getting drinks, right, at a store, right? And you can really see the variety of captions, right? The variety of different descriptions that can be associated with the same image, right? And that's what makes this task so interesting and so challenging at the same time. Right. So how do you measure how well the system describes images, right? Well, so as Larry said, we really framed this as a ranking problem. So for example, for image description, right, you have a pool of images. Sorry. You have a pool of unseen images and captions, and you want to rank the captions for each image. Right. The same for image search, right? Now you can take these unseen captions and you can rank the images for each caption, right? And then how do you evaluate this? Well, so the test pool, say, contains 1,000 images and their captions. Therefore, it contains the original caption of the test images. This allows us to then measure the rank of the original caption in this list of 1,000 items. And then we can report the recall at 1 or 5 or 10. So how often is the original item the first returned result, or among the top 5, or among the top 10? Right. Why do we use ranking? Well, we actually found that this really allows for pretty objective and directly comparable evaluation that correlates really well with human judgments. And unlike, say, in generation, all systems have access to the same pool of sentences, so it makes it much easier to compare different systems directly. Right. Here, just a few results from our old paper, right? So these are the first ranked captions for each of these images. Again, these are unseen, right? But quite often the system makes mistakes also. This is my favorite, that the basketball players in action. So numerically, how well does this work? So we were really surprised. We were really surprised that out of 1,000 images, 30% we would get, the original item among the top 10, right? That was at the time that was we didn't expect this to work so well at all, right? These are really old results. There are no detectors whatsoever. There's no neural nets at all. We just use pyramid kernels over very low-level visual features, just sift and texture and color, right? Nowadays, right, of course, we use deep learning, and the results have really, really jumped. But these are now results on Flickr 30K, but again, the same kind of 1,000 image test set, right? So now we're getting really much, much better results. But all of these methods are really very, very shallow, right? Couldn't we do better, right? Couldn't we actually use like object recognition, et cetera, right? The problem is, of course, that these data sets are generally completely disjoint from image description data sets, right? But perhaps with the exception of MS COCO, of course, right? So we really thought, well, we need data with much richer annotations that really links the captions directly to the images, right? So just recently, we've released a new version of our data set, which we call Flickr 30K entities, which augments the original data set with bounding boxes and co-reference chains for all mentioned entities, right? Again, this was done by crowdsourcing, right? So I just want to give you a few examples, right? So here's a particularly simple example, right? So the bounding boxes have the same color as the dimensions, right? So, for example, here's one really, really simple co-ref chain, right? But everybody mentions the man. Only 2 people mention the earring, right? Only 4 people mention the glasses, and so on, right? Everybody mentions this hat because it's really weird, right? But so now we actually have explicit annotations, right? But sometimes the annotations are much more interesting. For example, here, right, so the group of people, right, and the flags, they each refer to a set of entities, right? So we try to have bounding boxes for each of them, right? Plural mentions are particularly interesting because these chains may also intersect, right? So there are pictures where, like, say there's a couple and somebody mentions a man and a woman, somebody else mentions the couple, and so on, right? So there's actually lots of really, really interesting problems in this data. Right? So do these entities help? Turns out that yes. So here at the bottom, you see our results now on the same task, where we use the same kind of CCA technique as before. Now of course, with neural net-based vision features, where we just added the read and phrase pairs as additional training data. So again, there's no explicit detection going on at test time. We just trained the model on more data, and that really, really helps, right? Right. Even though that additional data is just essentially drawn from the same training data as before. Right. So does this mean that we've actually solved image description, right? I mean, like, we're really doing surprisingly well, right? You look at the results, they're pretty good, right? Are we done? Well, I really think that learning to associate images with these simple sentences that describe them is a much, much easier task than I think any of us would have thought a few years ago, right? This is really, really surprising, right? And I think a lot of this really good, has to do with how well vision works nowadays, right? These deep learning-based features are just really, really, they work really well, right? They're really helpful. But I think it's important to remember that we're really fooling ourselves, right? If we think that it means that these systems understand images or simple sentences, right? So couldn't we do even better, right? But what about richer linguistic representations, right? As I said, I'm really an NLP person. I would like to have a task that shows that you need rich semantic representations and so on. But so far, I think the jury is still out, right? I mean, like, so far. So yes, we're using lexical similarities. We're using sort of vector-based representations of words, right? But these are still pretty shallow representations, right? So, linguistically speaking, right? Unfortunately, I think the jury is still out, and I think this has to do with the nature of this task, right? But it turns out that there's just not that many kinds of sentences, for example, in your test pool about a particular kind of scene, right? The task isn't really appropriate to really tease apart these sort of fine-grained semantic distinctions, right? I think it's very, very similar when you look at generation, right? The kinds of sentences that are produced tend to be sort of fairly simple, right? I think we need sort of, now that we've made so much progress, right? We need sort of more challenging tasks, right? I'm not sure what such a task would look like. Here, I've got one idea of something we could do now that we have something like Flickr 30K entities, right? So, for example, here's a sentence and an image, right? And here are the entities, right? So we have a woman, a child, a swing, and another child, right? And we would like the system to automatically identify these entities with their bounding boxes, right? So can the system do that automatically? Well, here are the bounding boxes that it predicts. But then when you look at which boxes it associates with which mention, right, things, so it kind of works for the woman, right? I mean, at least it identifies the head. But then when you look at the two children, things go wrong, right? So she pushes a child, right? Unfortunately, we think it's the other child, right? While another child looks on, right? So it just gets these two children wrong, right? Well, the swing it sort of gets, right? But the two children might be sort of the difficult part, right? Is completely wrong, and that's really because the system doesn't actually understand the sentence, right? So I think in order to solve a task like this, we need to be able to really understand both the image, right? What does it mean to be the child that's being pushed, right? What does it mean to be the child that looks on? How does it look like, right? That's a much harder task than just saying the sentence which talks about a woman and two children in the swing. It describes this image, right? Right. So I think tasks like this text-to-image co-reference resolution may require actual language and image understanding, right? That aren't really being tested by the current task, right? So I don't really know what's next, right? I think we need more challenging tasks and better evaluation metrics that actually test the system's ability to understand images and language, right? We also need much bigger and more diverse data sets with much richer annotations. And of course, so MS Coco, that is a really, really great example, right? But we now have something much, much bigger than Flickr 30K, right? With similar kinds of crowdsourced annotations, right? That's really fantastic. We also have object annotations, although they're not directly linked to the to the captions. Right. So I really think that that the more of this kind of data we get, the more progress we can make. So I think it's a good start. I think we're so I'm pretty hopeful that there's going to be a lot more really, really interesting things to happen in the near future. So with this, I'd like to conclude and like to thank my students and my collaborators and my funders. And here are some of our references. So thank you.
Thank you, Julia. Are there any questions? If you use one of the mics, she'll be able to hear you. Anyone? No? Julia, on the co-references, so the when you did the co-references, how much of inner agreement was there in the mechanical checkers? Were the checkers, the humans themselves, agreeing on what was being referred to?
Oh, that's a great question. I don't have the numbers offhand, unfortunately. So we did a lot of quality control, but I would have to look up the actual internet annotator agreement numbers, right? I think it's difficult for like plural mentions, for example, right? So it's easy when it's just a picture of a man, right? That's easy. But it gets really tricky when there's, say, like a whole group of people and somebody mentions some subset and somebody else mentions another subset of the people. Right, so this happens particularly often in sports, right? Somebody mentions, I don't know, two teams. Somebody mentions two players from the two different teams. Somebody mentions one player and another player, and so on, right? So there's a lot of, so these chains intersect, right? There's a lot, and the different mentions in the different captions, and sometimes it's not really clear, right? So, but unfortunately, I don't have the annotator agreement. Yeah.
Okay.
Yeah. Thanks.
Testing. Can you hear this?
Yes.
Thank you for a very nice talk, and as an area I'm not familiar with, and I appreciate the introduction. So I have kind of elementary question. I may have missed something. So the captions that you're evaluating are all captions that were already entered by the crowdsourcing. Is that correct?
Right, yes.
So what's the status of just generating a caption for a new image from scratch?
I believe that Meg Mitchell would be a much better person to tell you about that. I think she's one of the next speakers. So just stick around.
The next two speakers will
we'll
cover that pretty well, I believe.
Yeah.
Right, any other questions? Yeah. All right, great. Let's thank Julia again.
Thank you. Thanks.
All right, so our next speaker is going to be Meg Mitchell. She is a researcher at MSR in the NLP group. Previously, she did a postdoc at Johns Hopkins.
There are several.
You know how many times Meg corrects me? I mean, you can tell she's NLP and I'm Vision, because I'm just like, wow, whatever. I also look at Meg as one of the pioneers in this language and vision space. She did it before it was cool. She did some really great referencing. What was it? How to refer to everyday visible objects. Yeah. You know, it was really, I think, well ahead of what the community was currently doing when she was doing it. So I'm really looking forward to the talk that she's going to give today.
Ooh, no pressure. Hi. So before I begin, it seems that probably all three talks are going to be looking at captioning. So I just sort of wanted to quickly say that this is a vision to language session. And echoing Julia's sentiment, there's a lot of parts to that. I think a lot of us who work on captioning don't see captioning as the super cool thing. It's actually a stepping stone to get further and further into artificial intelligence. So I want to make that clear as you hear more and more about captioning work. You know, in a year, this is going to be old news. We'll probably be able to get it, well, we're close to human performance now, let's say. And so, you know, take this talk as a kind of a historical note, but really why we're looking at this space is because we're interested in looking at that connection between vision and language. And doing simple denotative description is a first pass to see what we can actually get at. And really, I think a lot of us are pushing towards much further, richer, more interesting tasks in the future. Okay, so this talk is on the Microsoft Research Image Captioning System. This came on the heels of the COCO data set that Larry was working on. We had a bunch of interns who worked with us last summer who really made this come to life. Hao Feng, who's at the University of Washington. Saurabh Gupta, who's at Berkeley. Forrest Yandala, who's at, I don't remember offhand. And Rupesh is in Sweden somewhere. Yeah, I worked most closely with Hao and Saurabh. Hao worked on the generation and Saurabh worked on the image analysis, as well as a bunch of researchers who have been involved with this as well. And Jacob Devlin has recently entered as kind of a newcomer, right? So Jeanette talked about this in her talk, but one of the sort of long-held dreams of artificial intelligence is to be able to have computers understand things. And one way to look at this is in terms of image understanding. This is particularly interesting to NLP people because this is a form of grounded semantics. We can associate a word to visual properties, and then we can mine those visual properties in order to understand the context more deeply and what our expectations are about the word, not just in terms of text-based statistics, but in terms of what we see in the world. And Julia has this nice work she's cited in JAIR, the Journal of Artificial Intelligence Research 2013, where she breaks this down into perceptual, conceptual, and non-visual descriptions. And the work of image captioning is largely concrete conceptual descriptions. So these are specific descriptions which may identify people and locations, their names, basic description about what is in the image. And that's what we're focusing on here. Perceptual and non-visual descriptions, and then abstract conceptual is still to be done. Okay, right. So I'm going to talk a bit about previous attempts. As Larry mentioned, you know, I started actually working on this as a linguist in 2005, when I was just kind of, you know, I had a pixel and what do I do with it? You know, it was very naive at the time. But eventually, we got to a point around 2011 with the sort of current vision techniques then, where we could start saying things that kind of sounded human-like. We still had to use a lot of hand engineering. And one of the major problems was that visual detection just wasn't that good. So it was the job of the NLP to make up for their sort of errors. So there were two systems that came out like right before the deep learning revolution in computer vision. The Baby Talk system, which was spearheaded by Alex and Tamara Berg, and the Midge system, which I spearheaded working with the Bergs. And the top one in black here is where we are now, right? So back in 2010, we could say something like, here we see 3 bicycles and 1 road. The first gray bicycle is by the road and near the blah blah, and it kind of is sort of long, but we're starting to list all the things we see. And now we're getting to a point where we can say a group of people riding bikes down a city street. So we've come a long way very quickly, and I expect that we will continue to advance very quickly. Right. Jeanette may have stolen my slide. You guys already know who wrote the, which one is the robot and which one is the human, so I can skip over that. But the basic approach we took was, this field is exploding right now, and there are so many little parts that we can look at. There are so many aspects to how the vision information can be transformed into language, right? So when you're working with vision, you have this continuous representation, and you're working at the raw pixel level. When you're speaking in language, you're producing sort of discrete categories. So there's some sort of bridge that has to be crossed to get between these sort of continuous low-level representations and what we say in a sentence. So we broke it down into image analysis, language generation, and re-ranking, with the idea that each of these aspects are things that could have pretty nice algorithms to explore, and we could really dig into the problem. Although it's a bit of a bad word in NLP, we decided to do a pipeline system instead of training end-to-end, and this was specifically because we really wanted to dig into each of the little parts of the problems. We also have a trained end-to-end one. That's at ACL. It doesn't do as well. Okay. So the first step in this is image analysis. And the idea behind this was that the words that should be detected should not be up to some categories written down by someone, but can be figured out just by looking at the vocabulary and connecting that to the image. So what we do is we take all of the captions associated to each of the images, and each of those words in the captions are then possibly some sort of visual concept that we might be able to pick up. Right, and we ended up just focusing on the top 1,000 most common words, which ended up covering 92% of the data, with the idea being that we can look at an image and then maybe we can just get a sense of a ton of different sort of phrases and words that we can say about it. And then once we have that, maybe we can talk about it. Okay. So the first step in this approach was to enumerate the regions that we want to look at in order to think about what visual concepts might be covered. And so for this approach, we did brute force enumeration, where we just we made a sort of 565 I think it was like 224 by 224 box that we just sort of scaled across the image with a stride of 12, so that means like skipping over 12 pixels, kind of like this, right? So I'm in NLP, so this was novel to me. Maybe this is really, you know, everyone else knows about this. But this is the idea, right? You just kind of go through, you look at all these different regions, and each of these regions you can then train to see if it could possibly emit a word, right? And so you do this over the entire image, and then you have this really dense, basically grid over the image that corresponds to tons of really rich visual features. We sampled it at a bunch of different scales. So we had boxes that could incorporate other boxes, and from this we had 190 boxes per image. And then I'm going to say that we call it a bag of boxes, and this bag of boxes we can now use in order to try and output words. So we used a convolutional neural network, pre-trained from ImageNet, and then fine-tuned on the COCO data set. We ended up using VGGNet, which is state-of-the-art, is roughly state-of-the-art now. At least it was state-of-the-art like 4 months ago. It's moving very quickly. So we took that, fine-tuned it on the COCO data set, and then we said for each word and for each box in each image, we can basically compute whether or not there's possibly a word there, right? So this is just a simple logistic regression, and I think this is probably familiar to anyone who works on machine learning. And the idea was that we could use noisy or multiple instance learning in order to know what the general visual concepts were in the image. So in previous vision work, one of the difficulties, one of the main things that they had to tackle was the fact that you see tons and tons of incorrect detections all over the image. So our thought about this was like, maybe we can just look at some things we're pretty sure about. So for each image, we have this bag of boxes that I just mentioned. And then we can look at them in terms of positive and negative instances for each word. And then we can calculate the probability that some image as a whole manifests that visual concept using this noisy or multiple instance learning method. Right. We computed a global precision threshold, and we output all words above some threshold. We decided to look at precision at human recall, which I don't think had been looked at in vision before. But for every word, we can hold the recall at the human rate, so whatever the human rate for that word is, and then we can look at our precision at that point and threshold from there. So we do pretty well using the multiple instance learning approach, and this is in contrast to what most systems seem to be doing now, which is a full classification approach, where you take the whole image and shove it through. We broke the image down into a bunch of bits, and we found that we did quite well for both precision at human recall and for average precision. And here's some examples that we're using in multiple instance learning. Here's a cat. Here are a couple pictures of a cat. There are two on the sink there. There's one on the toilet. One of my favorite things about giving vision talks is I can put up pictures of cats, which is really, I can't do that in NLP as much, so that's pretty great. And here's its detections for red. So you can see that it's actually starting to localize these things really reasonably well. And we can leverage that to get a sense of the common things to talk about in the image. Right, okay. So the next step was language generation, which is closest to my heart. What the idea was, we want to leverage a language model, but we want to do it in a clever way. So the problem with using vanilla language models is that they tend to babble. The probability of a word depends on previous words. If you train a 4-gram language model on a bunch of Shakespeare, you can get something that sounds like Shakespeare. Unfortunately, it doesn't actually make a lot of sense. It makes sense locally, but not globally. So we thought about how can we be clever about this in order to have long-distance dependencies captured, to have global information be correct as well as the local information. And one word for this, like local problem, is we called the Malkovich problem, where you get into one state with one word and then you end up saying the same thing that you just said and you kind of recurse from there. So we wanted to get out of that sort of problem. So our thought on this was we can add basically a blackboard to keep track of all the visual concepts that we want to generate, and then encode that into our model. So instead of using a simple language model, we decided to use a maximum entropy framework where we can train discriminatively on the visual concepts as well as n-grams. So here we have this global view afforded by the multiple instance learning output. We remove a word when we generate it, and then we keep track of it in terms of the previous words that we've already said. And we stop generating once we've either hit end of sentence marker or once we've covered all of our visual concepts. And so from here, we get from the Malkovich problem to things that actually start looking really reasonable. So a kitchen with wooden cabinets and a sink. Okay, so to be very explicit about this, the maximum entropy language model just uses an objective function that's the log likelihood of the captions conditioned on the detected objects. Small note, we used noise contrastive estimation, so we didn't have to calculate the exact denominator during training. And we used n-gram features up to 4 grams. Here's our features right here. There's just a few, but basically this is keeping track of what the score from the vision system is. If the thing we're producing is in the blackboard, where we're keeping track of all the visual concepts, and if it's predicted by the n-gram statistics. For the generation process, we perform a left-to-right beam search. Truth be told, a lot of these ideas were originally outlined by Advait Rathnapakdee. If you look at his work, it's a treasure trove of cool ideas. So we were sort of playing with that. we maintained a stack of partial hypotheses, and this is pretty familiar to people who work in machine translation. This is a sort of simple decoding technique. From this, we form an M-best list, specifically the 500 captions that we think might be best suited to the image. And then we start to re-rank. We start to try and figure out which of these are the best. So you'll notice that we've only used local information so far. So the detected words come from the boxes local in the image. The caption is then generated word by word. But we haven't captured any sense of global semantics. How does this whole sentence match to the image? If we take the image and the sentence, can we say that this is like that, right? So the solution to this was to project language and vision to a common space. This is similar to what Julia has done. This is similar to what a lot of people have done. But we used a technique that we've been working on here at MSR. It's based off of what's called the deep semantic similarity model. Because I wanted to sell it to the CVPR researchers, I insisted we call it the deep multimodal similarity model. Unfortunately, that means that now there's something called the DSSM and the DMSM, and they basically are referring to the same thing, so I apologize, I didn't foresee that. But basically the idea is that we want to take a pair of neural networks, one for each input modality, and train them jointly. So we map images and fragments to a common vector representation, with the intuition being that if a picture corresponds to a caption, then the global vectors should be trained to be close, and otherwise they should be trained to be far away. And we use cosine similarity to measure the relevance between the two. So the loss function minimized during training represents the, well, maybe this is too technical, but it's the negative log posterior probability of the caption given the corresponding image. But the idea is we're trying to say that this caption and this image go together. All right. So we use the minimum error rate training, which is pretty common in machine translation, and it helps us to re-rank the set of all the captions that we're thinking about. And it just uses a linear combination of features. Specifically, these are the features, the length of the sequence. These are actually quite standard in machine translation, so we just sort of borrowed it from there, as well as some indicator features for whether or not N attributes were included. And we found that in general, including 4 visual concepts gave us a full, fluent sounding description of an image. Okay. Our results, these are a lot of numbers to look at. We talked about this a bit in the opening session, but I mean, we really just agonized over the fact that although we had all these metrics, we looked at perplexity, we looked at BLEU, we looked at Meteor. If you actually looked at the captions and how the data was changing, how the output was changing as we messed with different parameters, we didn't feel it was actually accurately capturing the changes that we were getting. And in fact, we found that human written captions got a BLEU score of 19.3. Our best system is getting a BLEU score of 25.7. So like, okay, clearly something's wrong here. We're superhuman according to automatic metrics. So we took a look at human evaluation as well, where we had the annotators decide whether one image with a corresponding caption was better described with caption A or caption B, randomized. And we found that our system was chosen as being the same as or better than a human description in 34% of the cases. Just for everyone's knowledge, when you pit a human against another human, you get around 70%. So we still have a gap to make up there. It's not 100% though. And we got a lot of help with the deep multimodal similarity model. Right. Okay, so putting it together, the overall procedure was to create the data set, which we gave rise to the Microsoft COCO data set, and then suddenly everybody everywhere was also using it and doing the same sort of thing, so that was like really exciting and exhilarating. We then did the image analysis, language model, and a re-ranker. We then were actually also able to test on a held out test set that was provided by the organizers at CVPR as part of this COCO CVPR challenge, captioning challenge. I'm not going to get too much into the metrics. I think it's a little bit more fun to actually look at the examples of what's going on. So briefly, this is the kind of thing that the Turkers were taking a look at when they were making their decisions. Sorry, they didn't see the underlying information, but they saw the output of this. I'm showing you what our system was actually thinking. So we get an image of a baseball player. We use multiple instance learning, and we eventually say we think there's some baseball in here. So we generate a baseball player. Here's what player looks like. You can see activations all around the pose associated to being a player, a baseball player. Throwing, so here it's focusing in on the leg muscle as the guy is getting ready to throw, right? And ball, here it's localized directly on the ball, and that's without any sort of direct annotation from us. So we eventually end up outputting something like a baseball player throwing a ball. A nice property of this is the interpretability of it. So this is what we see when we see man. We tend to focus on the sort of facial features here. The presence of a beard is a strong indicator. A man sitting in a couch, maybe should have said on a couch, with a dog, right? Okay, so how did we do? It turned out that there were a ton of different competing systems all doing the same thing with the same data at the same time. There ended up being a total of 15 different systems that ended up competing on the same held-out test data set. We submitted a couple, but this was Berkeley, Stanford, Google, Baidu, Toronto, UCLA, Montreal, just tons of people. And so it was really fun to take a look at the similarities and differences between all the approaches. What you notice here, though, is human is way near the bottom, right? So we're all doing great given our objective functions. Humans just suck. So maybe we're superhuman. Unfortunately, we're not superhuman, but we're getting close. So in the CVPR challenge, they went a little bit further, and they put this out to humans and said, what do you think about these? We ended up tying in first place, where our system had the highest percentage of captions that passed the Turing test, so thought to be written by a human, and the percentage of captions that are most similar to human description. We also submitted a second system where we took a gated recurrent neural network and did some forced decoding. That got us second place, but it also got the highest score on the average correctness of the captions. Okay. So just for a quick summary, we've developed a state-of-the-art image captioning system and explored several methods in order to look at all the different varied nuances at the interface of vision and language. But there are so many more things to do. As Julia mentioned, and I'm sure Richard will mention as well, we want language to become more rich, more nuanced. We want to begin incorporating background information and common sense so we know when things are super remarkable and when things are probably not actually happening. And we want to be able to start speaking and learning in real time, bootstrapping from there. Okay, and our relevant papers on this are at CVPR 2015 and ACL 2015. Okay, thanks.
Any questions?
So this is not a criticism, but I thought both of the captions for the tennis player were kind of lousy. And so when I saw
well, I should
this
show
morning,
you our and best list, because some of them are awesome.
So I wonder has there been any work done to take the kind of captions that you get from multiple humans and put them up and lie to the evaluators and just say, which of these is a computer, and see if people like them?
Oh, we did that. What? Yes. Okay, so I didn't talk about this. So one, we just did human versus human, and that got to one human was voted to be 70% equal to or better than the other human. We also did a nearest neighbors approach, which has been sort of standard baselines in a lot of vision to language work. And we found that a nearest neighbor approach is actually quite good at this. We still beat it handily, but not all systems that are being developed that are the end-to-end CNN to RNN kind of thing do beat the nearest neighbor approach. Oh, and this is really exciting. Read our ACL paper. The LSTM approach actually seems to be mimicking the nearest neighbor approach, so it seems to actually just be learning a nearest neighbor function, so it's kind of fun.
One more question in the front here. Right there.
Thanks. Once the system is trained, can you give some sense of how much CPU time it takes to classify or create the caption for one image? So,
Larry was just asking
how
me
real
this.
time is it, basically, once it's done?
Yeah. So I haven't timed it as clearly as I should. We did time it going back through a web server, like displaying and da-da. That actually took a full minute. I can just give you a vague estimate of around 20 seconds. Like it's not that fast.
Sure. And is that like a single CPU, many CPUs? Like what would that be?
Yeah, I think it's like a single CPU. We actually haven't tried to set this up for speed yet. So it's not very good to look at this for benchmarking speed because there's probably a lot of things we can do. We were just trying to see what it did.
Sure. Thanks.
Who was first? You guys know?
So I was thinking a little bit about Julia's example about the woman pushing the child and the other child watching, and just wondering about sort of asymmetric binary relations, like left of, right of, pushing, being pushed. Does that come out of what you're doing? How does that happen?
Yeah, so there's a lot of really interesting work we're doing on this. I don't know how much I should say. Some of it does come out. So one really exciting thing that I found that maybe people in the vision community disagree with was that the system started to be subitizing. So for numbers 2, 3, and 4, it's just recognizing that like an entity, and that's sort of unexpected. For the sort of asymmetric relations, I think that's probably one of our weaknesses. That's definitely a place where we can improve. We are good at looking at a couple things at once and saying something about it. So in the case of counting, right, we're looking at 2 things at once and we're able to say 2. But in terms of being able to say the specific relation, like this guy is left of that guy, we're still working on it.
One more question?
I had a question. Good talk. I had some application, like practical question. I don't know if you evaluate the impact of the global term. You had like this local term and the global term, and if you know what is the impact of adding all this global information about the images.
Yeah, so there's a few places. I think you're probably talking specifically about the DMSM, and those numbers are in the CVPR paper. But we get like a 2 or 3 blue point boost with the DMSM. So.
Okay, and also in terms of the size of the data sets, for example, if you double the size of the COCO data set,
yeah. We tried
what
this.
expect?
I mean, we didn't double it. We tried training on train and val, and then just testing on like a couple sentences, and then we actually put those up onto the official server for the held out test set, and we did not see a significant improvement. So it might be the case that, well, there's a lot of reasons, but yeah, adding another 40,000 captions didn't help.
All right, I think we'll stop there. Let's thank Meg again. All right, so next up, and our last speaker is Rich Zemel. He is a professor at the University of Toronto, and in his own words, he has interests in inference and learning in biological and artificial systems. In my words, I really look at Rich as being one of the people at the forefront of the language and vision trend right now. He's done some really cool stuff on attention modeling with language and vision, and he's also done some, from this morning, maybe slightly controversial work or named work called thought vectors, which maybe he'll be talking about today.
All right. Thanks, Larry. Okay. So really happy to be part of this session today, and the 2 speakers before me did a great job, both Julia and Meg, talking about image captioning. I'm going to talk about image captioning, but focus more on machine learning issues. All right. So, so I want to start. I know many of you are familiar with it, especially it was talked about in the first session this morning with the big success of so-called deep networks, these big neural networks that are trained on lots of data and to do things that are typically classification problems, where the idea is that for every input you have one particular target, and the aim is to classify that target correctly. So for an image, you might want to say, what's the dominant object in this image? And everybody knows, I think, that these have done remarkably well on things like speech recognition, object recognition. And the main aim in such systems is to generalize beyond the training set. You want to be able to take images that may be slightly different but similar to training images and classify those correctly. And so the success means that you're able to generalize. And so some recent studies have shown that these systems, despite their notable successes, actually don't generalize very well. They're in fact quite brittle. So somebody did a study where what they did was they took the images that are shown here on the left, and those were all classified correctly. And then what they did is they added a little bit to every pixel, so that's shown by a heat map in the middle, and they produced the images that are shown on the right. And in this case, it turns out that the same network that did really well in the images on the left classified all the images on the right as an ostrich. Okay? So the generalization was not so good here. Right? So that's an important aim from the machine learning world is to come up with high-quality generic representations, meaning that they're useful in lots of different tasks. And so what I'm going to talk about today are a few efforts, a few different things that I've done with my group, mostly with my students and also with some other colleagues, aimed at this idea of coming up with generic representations. And most of it concerns coming up with new objectives. So new objectives were talked about a little bit this morning as well, where it's not about these kind of supervised standard classification kind of objectives, but instead more unsupervised, based on things like image and text statistics and co-occurrences. So the first objective along these lines is one that has to do with context prediction, where the idea is you get an input that comes as a set of things, let's say a pair, and the aim is to take one item of the pair and predict the other. All right? And the standard setup for these kinds of things, as actually mentioned in a couple of the talks before, is that you have a kind of encoder that's going to map from the first input of the pair to some vector, and then take that vector and decode it to come up with the second input of the pair. All right? So that's the kind of basic setup you want to have in mind for most of the things I'm going to be talking about today. And this has been used very successfully. For example, there's a system where you feed it tons of sentences, and sentences that can come from things like books or Wikipedia articles or lots of things. And the aim of the network is to take a word and map a word to a vector, and then from that vector be able to predict both the word that comes before and after it and the word that it comes, 2 words after it and 2 words before it. And that's a so-called skipgram model, and that becomes a very useful representation for words. Right? So what we've done recently is abstracted this idea to whole sentences, so not dealing with words, but whole sentences. So we take this encoder-decoder model, you feed it as a sentence, and the aim of it is to predict the sentence that comes before it and the sentence that comes after it. So here you can have a sentence that says, I could see the cat on the steps, and it has to predict the sentence before it, which was I got back home, and the afterwards was this was strange. Okay? So that's our system that we've developed, and we call this skip thought vectors, and this was in fact the one that was spoken of dismissively this morning. But we're actually really happy with how it's working. Let me tell you a little bit more about it. The aim of it is, well, we train it up on 74 million sentences, and it takes about a week. To do this kind of prediction where we're predicting the sentence before it and the sentence after it. And then what we do is we want to show that this is actually a very useful kind of generic representation that's useful in all kinds of natural language processing tasks. So we took 5 different NLP tasks, things like semantic relatedness and paraphrase detection. And we showed that just building a simple linear classifier on top of these representations did very well on these tasks. It didn't beat the state of the art, but it was competitive with them. And all of the state-of-the-art methods in these cases used very kind of customized, hand-tuned features. The idea is we have a generic representation that's quite powerful and useful across different tasks. Right? So that's one example of this kind of idea of predicting context. Here you're predicting one sentence from the other. Another one is in the captioning work. So we want to be able to predict captions from an image. Like on the left, you want to predict the castle and the reflecting water from that image. Or you can predict an image from a caption, like the ship sailing on the ocean, that image from that caption. And so this is something that Julia spoke about, and actually Meg did as well. I won't spend much time on it. It's the same idea. We want to map to some sort of space, a joint space, such that things that are nearby in that space are related. So it's a kind of semantic related space. And we train it up using a kind of ranking objective where captions that aren't paired up with the image are actually far away. Okay, so that's the objective that's shown below. And then what we do to decode this, so this is the encoding. We map it to this space, and the decoding is a word-by-word generative decoding. So there was a question about that earlier. So we're actually generating words one at a time using something called a neural language model that generates a word and then generates the following word based on the words that have been generated so far, as well as this semantic representation. So that's the way we have been doing image captioning, and we've gotten pretty good results on that approach. Okay, so that's one kind of objective, this context prediction. A second objective is that we want to take this idea of generating things seriously. We want to actually look at the quality of what's being generated. And so in this case, for example, we want to be able to generate images that look like real images, right? And again, we want to be able to generalize beyond the training set. So we don't want to fall into the same trap I was talking about that the classification methods have, where you can kind of memorize the training set and do a really good job of generating realistic images, but all you're doing is reproducing the training examples. So the question is, how can you formulate an objective that allows you to generalize in this case? So here there's some recent work that's become quite popular, something called an adversarial approach. So you want to have an adversary out there, and the idea is that you're going to build a system that's going to generate a bunch of images, and you're going to put the adversary out, and the adversary has to tell which image was generated by the model, which one was generated, which one is real, which one was generated by nature. All right? And so this has been used to good effect recently. But there's an optimization issue that's a problem with these kinds of methods. And the problem is that the adversary is kind of adapting as your model is coming up with a new way of generating images. And then your image model creation is going to adapt as the adversary adapts. So it's a bit of a circular thing. It's like a dog chasing its own tail. And this type of thing leads to a hard minimization problem. And so they get a lot of local minima in this optimization. So we developed a different approach with a couple of my students where the idea was, it's illustrated here on the left. You want to think of, you have some, again, that H is some sort of vector space, and we're going to draw vectors randomly from some uniform prior distribution in that space, and then just run through a standard feed-forward neural network, deterministic feed-forward network, and produce an image as the output. So you might produce the things shown on the left side that look somewhat like handwritten digits. And then what we want to do is train those up so they look like the data, so that they actually look like real data. And the novel idea here is that we don't want to do this on an image-by-image example. Instead, we want to get the statistics right. We want to say, overall, the statistics of our samples should look like the statistics of the true data. Okay? Not that each image should match a given image. And that's what's going to enable us to do some generalization. And the way we accomplish it is using this, what we call the MMD, or the maximum mean discrepancy measure. This is something that comes from the statistics community. And I won't go into the details on it, but the basic idea is that you have, think of, you have two sets of samples. One comes from, in our case, one comes from the actual training set, and one comes from the model. And this is a distance measure that says how close are they, or another way of saying it is, what's the probability that they were actually drawn from the same probability distribution? So if they're drawn from the same distribution, then these two samples should be indistinguishable. Right? So our idea was to use this as an objective for training. So we want to minimize this metric so it looks like the two samples were drawn from the same distribution. And that has a couple good properties. First thing is that it's easy to compute. So that, it's a big equation, but it's actually very straightforward to compute. And the second thing is that it has exactly what we want, which is that if we can force this measure to 0, that means that the two distributions are the same and you can't tell them apart. And that means that, more technically, that they match in all of their moments. The distributions match. So the first order moments, the means match, the second order, the variance matches, and all the higher order moments as well. So if you can force it to 0, then you'll say that the samples look exactly like the data. So it's a very good measure to optimize for our task. Okay. And so this is the version of our model that works the best, where again we have this encoder and decoder part of it, and we have the generation from this latent variable h, this vector space, down to the images, and we try to make that look like the data. And we again try to get the statistics of the samples to be similar to the statistics of the data as measured by this MMD criteria. And here's a few quantitative results. So we compare what we call our GMMN, which is generative moment matching networks with an encoder. That's the bottom one. That's our best version of the system against a bunch of other models. And what we're comparing here is based on an estimate of the log likelihood of some held out data on 2 different data sets. One is the handwritten data set, the MNIST set, and the other one is a bunch of images of faces. And you can see that we do better than the other networks, other systems, including the adversarial networks I was talking about before. So this is some quantitative results. I think it's always more fun to look at qualitative results. And so here's some pictures. So at the top you see these are some of the samples that are drawn from our system that was trained on the faces. And you can see that they look somewhat like, these are just independent draws by taking the random vector, running it through the network, and producing an image. And then what we did is we wanted to explicitly ask about generalization. And so one way to do that is to say, well, we can take a generated image and say, well, let's try to find the closest image in the training set and compare them. And what you can see, so this is what's shown on the bottom. The top row are the ones that we generated. The bottom row are their corresponding nearest neighbor. And you can see that some of them are quite similar, but they're different. So they get the sense that we're making some progress on this aim of trying to generalize from the training set. Here's another view of what's happening. So another fun thing you can do is, so again, like I said, you generate an image by taking some random vector in this vector space at the top of the network that you're going to run through. So we can take 2 different vectors and draw a line between them. And for every one of those, each of the ones at the end and some evenly spaced points in between, we can generate an image. And that's what's shown here. So if you see the one in red in the corner, that's one randomly chosen point in the image that corresponds to it. And then 2 rows below it, there's another one that's highlighted in red, so that's the other chosen point. And then along the way, we can generate images that go along those points in this vector space. And you can see you get some interesting behavior. So from the second one down, you can see it starts at something that looks a bit like a 2, and then it kind of morphs into maybe an 8, and then a 3, and then it becomes like a 0. Okay, so it seems like we've captured something here. That's in the digit data set. So we do the same thing on the faces. Same idea. Choose a random point in the space, generate an image, choose another random point, and then generate images all the way along for, I think, like the 25 points in between, and those are the kind of faces you get. Okay, so it does some sort of interpolation. It's interesting. Simply it's captured some of the variations what I was talking about that naturally underlie the data set. So in this case, there's things like lighting and gender and mustaches, various things that are variations in the image space. Okay, so here we think we're getting at capturing the kind of underlying manifold in the image space. Okay. So the third objective, the last one I want to talk about, is one that I think it's something we've just started working on very recently. And in this case, we want to go beyond this. We want to extend, not just generate, let's say, one image, but generate a set of related images or a set of related sentences. And here it's not really about necessarily saying that we want to have a powerful representation. I think that this is just an interesting case in and of itself. The question is, there's a lot of things in AI that are basically inherently ambiguous questions that we want to be able to tackle. So I think this is a fundamental AI question. So an example is image segmentation. All right. So here you have an image shown on the left, and you have 2 different segmentations. The one in the middle, you see they have a segmentation where the top of the image is fairly well, the regions are fairly well segmented, but the person's kind of ignored what's happening in the foreground. And the one on the right, a different person, a different segmenter, annotator, has instead paid a lot of attention to what's going on in the foreground and hasn't done much in terms of the background. And both of these are perfectly valid. So I think of this as, the task of segmentation has some ambiguity. I think of it as a kind of one-to-many problem. You have one image and many valid segmentations. Similarly, when you generate captions, it's the same thing. You have this, and so this was mentioned, Julia mentioned this earlier. You have an image shown on the left, and you can generate two things, at least two things, a car on a beach with a boat in the background, or two hilly islands in the water. Again, both of these are valid. So we can think of this as a problem of diversity, and people in this audience know I've worked on diversity as a interesting question in and of itself. And one thing that we can get at here is what's the appropriate level of diversity in these kinds of one-to-many mappings? What are the kinds of things we want the captions to be diverse? In what ways? And the nice thing is that we have data available to help us answer this. So for instance, the MS COCO data set that was talked about earlier, it's been a great resource for the community. There you have tons of images. Each of them has at least 5 captions. So that gives you some diversity per image. And in fact, there's a subset of them that has 50 captions per image. So that's a lot of potential, a lot of one-to-many, where many being 50 in that case. So that's a very good learning set for this one-to-many problems. And our approach to this is to take what I was describing before, our moment matching network that goes from some vector space down to the output space. In this case, the output space could be a caption, not an image. But now we're going to condition on an input, where the input will be a particular image. All right? And we've also reformulated our objective. So the aim is no longer to match the statistics of all of the images to all of the captions to all of that we generate to all the captions in the data set. Instead, it's very input dependent, or image specific in this case. We want to take, let's say, the 5 captions that exist for that image and look at the statistics of those 5 captions and match that with the 5 captions or set of captions that we're going to generate from our system. Okay? So that's the aim, is to do it on an image by image basis. So this is some recent work with some of my students, and the details are it takes like 6,000 training images in one of the Flickr data sets Julia mentioned. Each one of them has 5 captions, and so we want to get the statistics of those 5 captions. Our system's going to generate a bunch of captions and get those to match. Right? And I could show you a few results here. The bottom row is looking at the blue score, which is a measure that a few people have mentioned. And what you can see without looking at, so our method is shown in blue, and the green method is a nearest neighbor method. And so this illustrates something that was also said, which is nearest neighbor methods do great on image captioning. So in some sense, we aren't doing as well on blue score. But if you look in a different space, like the vector space of semantic relatedness, which is actually using our skip thought vectors that I talked about earlier, our system, as shown in blue above, is actually beating all the other methods handily. And I think that's a better measure for, blue score has a lot of flaws. I think our skip thought vector is a better way of saying how related sentences are. And now, just for fun to actually see some examples. So this isn't, you won't be super impressed with our results here, but they're kind of, so here's an example I chose that are more just fun rather than the best results. So I don't know if you can see it. There's a dog, or a weird looking dog with a bunch of tennis balls, and you can see some of our captions there. And you can see that the captions are plausible and actually capture some diversity. Here's another example, one of my favorite ones, just because it's a strange image, but also you can look at some of our captions. And in fact, here I think we capture something interesting, right? So part of the caption is focusing on, you can see it says it has a colorful costume. So our captions are the one at the top. It says a blonde woman in a colorful costume. It's not quite right, but it's somewhat plausible. And then the one underneath, the female performer with the rainbow wig, instead of looking at the costume, it's focusing on the hair of the person, which plausibly could be a wig. And here's another case, a basketball player with a few of the captions that we generate. Right? So to wrap up, I want to go back to my claim. A real strong representation is one that can not only do recognition for objects and words, but can model the inputs in their context. And as I've talked about, a few objectives that get at that, trying to predict context, sentences from sentences, and captions from sentences, and vice versa. And also go further, be able to generate distributions of images, or in the last case, generate distributions of sentences that may be specific to an image. And the last thing I want to talk about, a little bit of where we're going with this. So how do we actually leverage these generative models? And so one thing is to gain insight into the model behavior. And Meg mentioned this. So one thing that we've done is look at an attention-based system. So the idea in the attention-based system is now when you're going to generate captions, you aren't going to generate a caption based on the whole image. Instead, what you're going to do is look at specific regions in the image. And every time that the system finds a region in the image, it's going to generate a word for that region. And then it's going to move to another region, generate another word. Okay, so we have this attention-based system. And if you follow along the bottom row, you have the image shown on the left. And you can see that it kind of looks down and it says, to the left it says bird, down below flying, over a body of water. Right? So it's attending to different parts of the image and generating words specific to those parts of the image. So that's something that we've run. And actually, so in the competition that was just mentioned at the end of Meg's talk, this is done with some colleagues in Toronto and also in Montreal. And this system didn't place in the top 5. It was like, I think, 6th or 7th maybe on the some of the metrics, like the blue and cider and these other metrics. But when we came to the human evaluators, actually our system did quite well. In fact, I think it was the only one overall that was in the top 4 that wasn't one of the industry-based things. So that was our little, we were happy about that. Some other things we want to do is try to leverage these generative models, see if we can actually improve classification tasks. And finally, we're turning our attention to things like video and trying to do the same types of things now on video. That's it. Thanks.
I have 2 questions.
Okay.
Both in terms of some of the issues discussed in the morning's panel discussion.
Yep.
The first one is that the way you train your moment matching network, it struck to me that you actually do use the supervision, right? Because you match with the statistics and use that to do the training. So that to me is more like
right. So there's an interesting semantics to this of what does supervision mean. So supervision in that case, though, we aren't actually required. So typically you think of supervision as some human has to come into the loop and add some labels.
Okay.
Right? So labeling being like the fact that this image contains, a hippopotamus or something.
I'll call it distant supervision.
Right?
So not the real question is that I remember you were one of the authors for this paper, awake sleep algorithm many years ago. Right?
That's true.
So and that was actually purely unsupervised learning, modeling the data distribution.
Right.
So do you compare these?
So this is still all we have is the data here. The difference, like I was saying, in some ways the difference is you have an image, and in one case you're trying to reconstruct that particular image. So that's your standard kind of generative model. Instead, what we're doing is saying, forget about the single image. You aren't actually trying to reconstruct the image. Instead, you're measuring statistics on the entire data set of images and trying to match that.
Okay, so
there's no additional supervision signal. It's just kind of recasting the objective.
Okay, so you believe that this way of training based upon moment matching is better than deep sleep and
yes.
algorithm? Okay, have you compared that, or is it just
so,
speculation?
So far, the wake-sleep algorithms, I think there are some very good methods recently for doing that, or recent versions of the wake-sleep methods, recasting of them that work quite well. Things like called variational autoencoders is one name, if you're familiar with that. Yeah. Those do quite well. But I think that they haven't shown the ability to do quite the same kind of manifold representations that we are. They're able to do things in other spaces, but I think that, so the two of them have different strengths, I would say.
Okay, good. So the second question, I'm sorry.
Okay.
The second question is that, so have you ever tried to use your skip thought vector as the feature extractor to fit into another, classifier, so that you can do some classification tasks? If you believe
that's what we were doing in the NLP tasks I was talking about. We were taking sentences and we were using these as mapping them to this vector space, and then those vectors were the input to some simple linear classifier for one of these, one of these 5 different tasks I talked about, like semantic relatedness or different things. Okay. So that's exactly what we were doing in that case.
Are you able to beat the end-to-end learning without using?
Yeah. So it's like it's not completely. It doesn't beat the state of the art, but it's competitive.
Okay, great. Thank you very much.
Another question?
I'm just trying to get an idea for scale here. You said early on that one of these, the training time for one of these problems for the 74 million sentences or whatever was a week.
Yep.
what kind of process was that, and what kind of system was it on? Was that parallelized and not on a big enough system? Is it on a serial computer? What did you do?
Yeah, so that wasn't highly optimized, or it runs on GPUs, but it's not running. We could definitely optimize that and run it much faster and farm it out over many more processors. It hasn't been optimized for that at all. And in fact, it's gotten better now. We're over like over a couple 100 million sentences, and can train it in a couple weeks. But clearly that can improve. We haven't just spent effort on that right now.
Any other questions? Nope. Okay, let's thank Rich again. And that concludes the session.